What's cracking, guys? This is the second video in the machine learning coding series, and I'll be covering Facebook DETR, so that's a short for detection transformer. And some of you might recall that I've already covered the paper in great depth, I think a year ago. So if you're not familiar with what DETR is, maybe consider checking out that video first. But I think this one will be like self-sufficient as well. So as I said, it's a model for object detection, and just for those of you who are new to the channel, object detection is this task where you have some salient objects in the image. As you can see, we have some cats and remote controllers here, and you can see that we have a bounding box around this cat here. And we also have a label associated with the bounding box. Similarly for the remote controller here, for the second one here, and for the other cat, this blue box. And finally we can see a purple box around this whole image, and basically the class being couch, which is the correct class in this particular case. So what I've done is I went ahead and basically cloned the official repo. And as I said, I'm going to walk you through the code base in a lot of details. Before we go there, I want to quickly walk you through the pipeline on the high level so that you have a mental model going into this video. The model itself is fairly simple, and we'll be focusing on three components in this particular video. So first is understanding how the actual architecture works. So how do we basically... Let me take a pen here. So how do we do this transformation here? How do we go from the image all the way to this set of box predictions? So understanding the architecture of the actual model. The second part is, given the predictions, given the bounding boxes predictions and the associated classes, how do we match those with the set of ground truth bounding boxes here? Okay, so basically what this model outputs, as we'll soon see, is, and this is a hyperparameter, but the model they've used 100 as the default. So that means we're always outputting 100 bounding boxes. And so we'll have two vectors as the output from our model. One is going to be 104. So that's going to be our bounding boxes. Obviously, the four points are enough to describe the actual bounding box. The format is, I think, first the center point coordinates x, y, and then the height and the width. But that's less important. The second vector that the model will output is just like 100, basically containing the classes of those associated bounding boxes here. Now, as I said, the hard part will be how do we match these outputs with like correct ground truth bounding boxes. So imagine we have this red bounding box represented as this red square, and consider we have I'll just pick another color like green because I don't have yellow at disposal. So imagine this yellow is this green, and so the idea is how do we know that we need to connect this one with this particular ground truth bounding box, and how do we know that we need to connect this red one with this red one here. And also we need to take all of the other predictions and map them into this no object, into this special class, the no object class. And okay, so that's the step number 2. And the way they do that is using something called Hungarian matching algorithm. We'll see how it works in a very in a lot of details. Finally, once we have the matching, we now need to calculate some sort of a loss and then do the backprop. So they'll have 3 types of losses. The first one is going to be the label loss. So that means for the matched boxes, we want to make sure that the probability of the ground truth label is as high as possible. That's first loss. The second loss is going to be L1 loss. So basically, how far off are our predictions from the associated ground truth boxes. So imagine we have a prediction here, and imagine we have a different prediction, the ground truth prediction being here. We calculate the L1 loss, and I'll get into the details of how that's calculated, but basically, you just treat the bounding box as a 4-dimensional vector, and you just find the L1 between the difference of those two vectors. That's how we calculate L1 loss. And the final one is the generalized intersection over union, which is basically a fancy version of your of the classic IOU metric. IOU is just a way to So what it does is it finds the area of this intersection here, and it basically divides that with the union, so hence the intersection over union. And you can imagine that as this tends to 1, that means that these two boxes are completely overlapping. And you can see as the less the overlap, the smaller the intersection area, and and when you divide that by the actual union, that goes towards 0 as the boxes don't. So yeah, it will be ultimately equal 0 once we don't have any overlap. So that's the third type of a loss. Again, don't worry if you didn't understand everything. We'll go into a lot of details in this particular video. Okay, let me just show you a bit more detailed view of the architecture here. So the idea will be to encode. So we'll pass first we pass the image to a CNN. We get some set of image features. We're going to then basically tokenize those image features. So we'll just treat them as tokens for the NLP transformer. So that part is here. We'll have some, so basically I said we're gonna pass them here and then encode them using the encoder stack of the transformer. We'll add some spatial positional encodings. And on the other hand side, we have this very interesting thing going on. So we have these, let me just change the color. So we basically have these object queries, which are going to be learnable, like 100 learnable embedding vectors. And it's 100 because, as I said, that's just a hyperparameter. And because we have 100, we'll also have output 100 bounding boxes. And you can see here what happens is that in this middle layer of the transformer layer, we have cross attention going on. So we have that these object queries are basically, each of them are attending to this encoded version of the image features, and each of them are looking for something in the image. So that's how, on a high level, obviously very hand-wavy, how this pipeline works. Once we get the output set of 100 tokens here, we just map them individually using MLPs or just a simple linear layer, and we map. So we take this token, we map it into basically a class. So we'll have associated class, and we also map it into a 4-dimensional vector here. That's going to represent the bounding box that this particular token encodes. And that's it on a very high level. With this prerequisite knowledge, we can now jump into the actual Jupyter notebook. So let's see what's going on here. Let's start from the beginning of the notebook. I'm just going to run these imports here. I'm going to import the necessary libraries. We're going to be working with PyTorch. Because this is Facebook after all, or Meta as they are now known to as. Here is a small minimal implementation of DETR. It's not as complicated, and it's not the same as the one they actually have in the official code base, but it's good enough and it gives an understanding of what's going on. So I'm going to run the cell and then explain what's going on. Again, quickly, we have a backbone, ResNet 50. We have this conv layer, which is going to take the 2048 channels of the output embedding volume from the CNN and just reduce the number of dimensions to 256, and that's going to be the ultimate dimension of the tokens that we pass into the transformer. So let me quickly just kind of explain what that exactly means. So as I said, we have an image here. So this is an image. We have a CNN block here. I'm just going to denote it as a box here. We pass the image, and out comes some volume. Basically, obviously the spatial. So here the spatial extent was, we had 3 channels here. So this was 3 here. And after encoding it through a CNN, we're going to end up with something that has like a smaller spatial extent. So let me try and denote that like the following. So basically we have a smaller spatial extent, but then we have much more channels. Okay, so something like this. I'm really bad at drawing today, so something like this. Basically, this number of channels here is going to be 248 for ResNet 50, and this is just like your downsample spatial extent. So this is like small h, small w, whereas this was like big H here and big W. So the convolutional layer I just mentioned has the kernel of size 1 times 1, which means it is just going to reduce the number of channels of this volume here from 2048 into, I think, 256. And then the idea is to just like treat these as a set of tokens. So we can, in a raster order, we can just do the following. we can just do this, and we take this vector. This is going to be the first embedding vector, which we pass into the transformer. Then we take the second one here. So this is going to be the second vector. This one here is the second one. And so, yeah, we basically do that in the rest order. Let me kind of zoom in here a little bit and show you what I mean exactly. So this is vector number 1, vector number 2, vector number 3, vector number 4, 5, 6, etc., etc. And that's basically how this part of the pipeline looks like. Okay, let me go back to the code. So that's what this conversion layer does. Then we have a simple transformer. Again, encoder and decoder stacks. And finally, we have the two linear layers, linear class and linear B box. I showed you what these do. These take the output embeddings from the decoder and just map them into either the distribution over classes for the Cocoa dataset, or this second one just gives us the bounding boxes for each of the output tokens. Okay, output embedding vectors. Here are the query vectors, the learnable query vectors. We have 100 of them. And that's it. And finally, we have row embed and col embed. These are just going to be the positional encodings. Okay. And once we do, so here's how the forward path looks like. We basically pass the inputs. So that's a set of images. We pass that through the comp1. Then we apply some batch normalization, ReLU, max pooling, whatnot. Then we apply the 4 layers of the ResNet 50. And finally, we apply this convolutional layer where we basically reduce the number of dimensions, as I previously mentioned. And what happens here is we construct the positional encodings. Then we're going to take those positional encodings, just sum them up with these tokens here. So that's this part here. Don't worry about the actual details. We'll get to those a bit later. So what is important is we have some tokens from the image. We add the positional encodings. We pass that into the encoder stack, and then through the decoder we pass the query embedding vectors. That gives us as the output a set of embedding vectors here, which we then map using the linear class and linear B box linear layers. We additionally apply sigmoid because we want to have normalized bounding box coordinates. So from 0 to 1. Okay, that's it. Now, let's see what happens. Let's just run this cell. It's going to load a pre-trained DETR model. So I'm going to just run this. And here we're just going to run this cell that defines the classes from the Cocoa dataset and some associated colors, which are going to help us visualize stuff. So again, the number of classes in Cocoa is, let's see what we have here. So if I add a code cell, let's print the number of classes. So shape, well, shape will not work because this is like a list. So we're gonna do length instead. So length, and this should be, I think, 91 or 91, yeah. 91, and then we'll add the additional no object class. We'll see that a bit later. Okay, here's some helper functions. This one helps us just do some type of processing to the input images. We do some resize operator. Then we convert the images into PyTorch tensors, and then we do ImageNet normalization. So these are statistics calculated from the actual ImageNet dataset. This is going to be like the mean, and this is going to be the standard deviation statistic calculated over the ImageNet dataset. These helper functions just map, as you can see from the format, CX, CY, WH, which is you specify the center coordinate of the bounding box and the width and height. And instead of that, it's going to convert it into a format where we specify the top left point and the bottom right point. And those are obviously equally informative representations that take equal amount of space. It's just that this representation is a bit more suitable to some of the APIs they're actually using, and we'll see that later. Not that important. Rescale boxes. So as I said, we do predict the bounding boxes which are normalized, which means from 0 to 1. This is just going to return, map those predictions into the original input image space, range. Okay, did we run the cell? Let me just run the cell. And finally, we have the detection function. Here what we do is we pass an image, we apply the transforms we just saw, we unsqueeze so that we add like the batch dimension. So this adds a dummy batch dimension 1 because that's what PyTorch models expect. Just some error checking. We pass the images through the model, we get the outputs, and finally what we do here is we take the prediction logits, we apply the softmax because remember, this is just going to apply a linear layer, so these are still unnormalized logits. So we apply softmax. After we've normalized the logits using softmax, we just extract all of the classes except for the noObject class here. That's why we have up to -1. And then what we do is we take those probabilities, we find the max across all of the 100 outputs, and we find those predictions where the peak of the distribution across classes is at least 0.7. In that way, we kind of take out only those very confident bounding box predictions, okay? That's the idea there. And then we use that vector, the keep vector, to basically extract only those bounding boxes, and then we just rescale those and return back the bounding boxes. We additionally return the associated probabilities here. So if I run this, and if we run this here, we're going to get as the output the scores and the bounding boxes. So let's kind of quickly examine what's going on here. Let's see what the shapes are here. So if I do print score shape, that's going to give us 591. So it's 5 because only 5 of the 100 bounding boxes were like confident enough. And if I was to print the boxes, this should be what? This should be 5, 4. That's the expectation. So let's run. It's 5, 4 indeed. So 5 boxes that are good enough. So I'm gonna quickly just modify this and return back like this the probabilities vector. So this should contain, if I'm not wrong, so let me just actually return back this original output. So like this, and I'm just gonna call that logits. So I'm gonna run that cell, I'm gonna add a logits variable here. So just add logits, run that, and see what the shape of that thing is. So that should be 191, I assume, right? So if I were to run this, we have 192. So it's 192 because, as I said, here we extract the noObject box. So if we were to take this probus, whatever, like it's a weird variable name, if we were to take that variable and return it instead, that's going to give us 91 instead of 92. So let me show you here, and as you can see here, that's pretty much it. Okay, now we can finally visualize what's the output of this function, detect function. And what we do is we iterate over this over the probabilities, over the bounding boxes, and we just plot rectangles using the coordinates from those boxes, and we plot the basically the most probable class from the distribution there. And if I were to run this, I mean, we already had the image, so let me show you. This is what we get. So this is the image with which we started this video. I showed you this one in the beginning. Okay, so far so good. Let's now jump to the second notebook. This was just like a quick, like a high level overview of how minimal implementation of a DETR could look like. And it turns out it works already fairly nicely. Let's now go to this one where we're gonna see some attention visualization. So I'm gonna again run the necessary imports. I'm gonna again run the Cocoa classes here. We have the same type of helper functions, the transform functions. We have these functions that change the box format. They do the rescaling, so I'm just gonna run those. Again, we have the same plot results function as from the previous Jupyter notebook. The details are not important, it's just like your matplotlib stuff. I'm gonna focus on the core and the gist, and that's the actual DETR model and how those three components that I showed you in the beginning of the video, so that the architecture, the Hungarian matching, and the loss calculation look like. That's gonna be the focus of the video. Again, let's load some of the pre-trained models here. We set the model into eval mode. So eval, just for those of you who are not familiar with PyTorch, sets. So that's very important because some of the layers, such as batch norm, behave differently whether they are in the depending on whether they are in the train or eval setting. We did the same thing. We just load an image here, and then we have a similar type of a forward prop as in the previous detect function from the previous notebook. So we just pass the images, we transform them, unsqueeze them, pass through the model, we get the outputs. We do the same type of transform here, so we get the probabilities. And this time the threshold is a bit higher. We use 0.9 here, although I think I'm the one who modified this, not sure. Let's assume this is 0.9, and then we do the rescaling. So let's see what we get. So yeah, for the most part, this part was the same as in the previous notebook. So we get the output predictions. Now that we have all of that calculated, let's go and add some hooks to our model. So what the hook does is, as the image is passing through the actual DETR model, we're going to log certain activations. And the ones we are going to be interested in is going to be the activations from the actual backbone model. So that's going to be the COM features. Let me show you what I mean by that. So it's going to be, we're going to log these features here, better yet. So we're going to log actually these features here. And we're going to log some of the basically attention coefficients, I think from the, I think from the multi-head attention, like the cross attention component here. So let's just make sure that's the case. So we take from the encoder, from the last layer of the encoder, we're gonna grab the self attention module. So that means we're going to grab from the last layer. So as you can see, we have n here. I think in practice they use 6. So from the 6th one, we're gonna grab the activations from this module here, okay? Multi-head self-attention. In particular, we're gonna take the matrix, like when you multiply query vectors with key vectors, you get a matrix of scores, which after you apply the softmax, you get basically the attention scores. So that's the one we're gonna visualize. And the second one, if I'm not wrong, I think it's this one here, but let's double check. If I go back to the code here, we can see we take the decoder, the last layer of decoder, multi-head attention, and I'm fairly sure that's the second, the cross attention one. So let me quickly go to the transformer file here. Let me just make sure that's the case. So transformer decoder layer, we are going to have, let's see, so self-attention and multi-head attention. The multi-head attention is the second, is the cross attention layer. Okay, so we are basically taking the activations from this particular multi-head attention head. Okay, not head, but the module, sorry. Okay, let's go back. That's enough rambling. Let's go back to the notebook. After we attach these hooks, and this is just your PyTorch syntax, I will not get into details there, and we run the inference. All of those are going to be logged in the associated lists. Then we just remove the hooks, and then we extract the 0th element from the list, because here, as you can see, we just appended. So by doing this, we just extract the collected data. So I'm going to run this cell, and let's see what happens. Okay, so we end up with those shapes. I'm going to quickly analyze what's going on. So COM features, let's print what we get here. So what I expect is, I assume something like the following shape, like maybe 1, 2, 48, and then some spatial extent, which is going to be, I think something like H is going to be 19 and W is going to be 29. That's less important, but let's kind of print this and see what we get. Okay, so we get that this, oh yeah, I remember. So there is this particular detail of the implementation. So we have to actually index, we have to index by this key, and only then do we actually get the, okay, and then we have to do additional tensors, because additional implementation detail, because this is going to give us nested tensor, and we just want the tensor info. So finally, okay, this is what we get. As I said, I kind of missed the small h and small w, but that was not the point. The same overall format is as we expected. let's copy paste this and let me do the following here. I'm not sure whether this is going to be nested vectors. So let me just try and do shapes like this. I'm going to comment this out, see whether this works. And it does. So 850, that's the, as I said, the scores, but what you get by multiplying the queries and the key vectors. Similarly here, if I were to do this and we're going to visualize the detection attention weights, let's see the shape here. So we're going to have, I guess, the same exact shape. Oh no, actually it's 100 because here we are in the decoder stack. So because of that, we have 100, 850 because we have 100 query, the learnable vectors, and we have 850 keys from the encoder stack. That's why we get this different shape. It all makes sense. Nice, we've seen the shapes. Now let's visualize the attention. So we're gonna, in particular, focus on visualizing the decoder attention weights. And as you can see here, they just grab the height and width from the com features. That's gonna be the 2534 here. And they iterate through the bounding boxes we previously predicted. So the 5 bounding boxes we previously predicted and visualized above here. So these are the 2 remote controllers, 2 cats, and a couch. And they are then going to, as you can see here, grab a particular index. So remember, this is going to be of the shape 100 because we have 100 query embeddings, and 850 because we have 850 of the basically keys coming from the image features of the through the encoder stack. And so this is going to grab 850 coefficients that basically correspond to the scores that this particular query vector has when it attends to the keys. Okay, just to quickly clarify what I mean by that is it means the following. Basically, so again, remember we have encoder output here. So we have basically 850 outputs here. And then we have the decoder stack here. And as I said, we grab the cross attention layer. And that cross attention layer has 100 query vectors. We have in total 100 query vectors there. And we take a particular one that's associated with the bounding box we care about. So we take, for example, we take this one here. And we see how that query vector, basically we do the dot product between that query vector and all of these key vectors. And those are the 850 numbers that we're now going to visualize. Okay, that's the basic idea. So let's see what we get. So after we do that and run this cell, we have this. So for this particular remote controller, you can see that this is the pattern that we attend to in the these are the image features that we attend to, and you can see there is obviously a correlation between these two. Similarly for this image here, similarly for this is, I guess, the couch, and so we are basically attending the ends of the image. That's how it figures out that this is the couch that we are seeing, and then you can see kind of a faint figure of the cat here, and finally similarly here we can see a faint figure of the cat here. Okay, so hopefully this gave you some understanding of what's going on, and that I hope that this image here helped you understand again what's going on. So let me just recap one part. So the shape here is 2534. If you multiply those two numbers, you get 850. That's why we have 850 here. So 2534. So remember that we started here from the image features that were precisely 2534, and then we took those in a raster order and we kind of flattened those out, and that's how we got these 850 tokens. So that means by attending to these 850 tokens, you're actually attending to the original image, but just a downsampled version. That's why we are able to get these interesting attention maps here. So that's how you connect these 850 with the images we get here. So with these images here. Okay, so yeah, that's the best I can do for now, but bear with me, we'll understand all of the details a bit later. So what they do here is they just plot print the shapes, and we saw all of this already. So I'm just gonna skip through all of that because we already saw it. What they additionally do is they take now the encoder attention weights instead of decoder ones, and they just reshape those such that we end up with 25, 34, 25, 34 instead of with 850, 850. So this is just going to be a bit easier to understand what's going on when we index into this array, into this tensor. Okay, let's now visualize the encoder attention patterns. So they grab 4 points from the original image, and then using those points, they're going to visualize the encoder attention. So let's see what exactly happens here. So you can see original image, they picked 4 points denoted here by these red circles. And then we visualize where these points attend to in the original input image, because we have the self-attention in the encoder layer, which are the image tokens, and that's why we get these image patterns. And you can see the interesting fact about DETR is that the encoder already learns to do some sort of instance segmentation, which is super useful if you later want to create bounding boxes around those objects. And this was not explicitly trained for, so this is just something that emerges from the way that DETR was trained, which is super nice. So let's kind of dig through this code and understand what's going on. It's a bit messy here, so I'm gonna just keep it on a high level. Basically, they create a bunch of subplots that's not that interesting. And then the important part is, let's see. So the important part is this. So we have image show of the attention pattern. So we take the index. So indices are again the points we picked, right? And so we grab those points. Those points are initially in the image space, and so because of that we want to downsample, because that's what the conv layer does. The backbone is going to downsample by 32. That's why we divide by fact, and this fact is going to be equal to 32. That's how we get the indices for the downsampled image features, and then we just basically grab the points and index into this attention tensor. Okay, and by doing that we basically figure out the following. I'm gonna again use my OneNote because this is very hard I realize this can be hard to understand by just me speaking about it. So what we've done is the following. So again, remember we have this volume here, and so what we're going to do with it is the following. So this is our volume. These are our tokens, basically. So this is the volume that came out from the CNN. So we take a particular point. So let me kind of create a grid structure here, so make it easier to visualize. We take a particular point, so this one here. So that's, as you can recall, that's the token that is fed into the encoder transformer. So somewhere in the transformer, we're gonna map this into a query vector, and then we're gonna take that query vector and basically do a dot product with the key vectors of all of these other tokens, right? All of these other tokens. And by doing that, we basically understand how this image token is attending all of the other image tokens in this volume here. So that's the idea. By the way, obviously this is flattened in the actual transformer. I'm just visualizing this as in this spatial format, just because it's easier to map what's happening here and why do we have the images that we get here. So hopefully that was somewhat understandable. And now this final cell just makes this basically interactive, so you can pick your own image and do the same thing in an interactive fashion. So if I were to run this, they created this nice widget where you basically have, let me show you what happens. So you can see here, you can kind of move this red point here, and you can see how the attention patterns change. So if I were to move this a bit more directly onto the cat, well, we get some weird patterns. So apparently when we are closer to the boundary of the cat, that's when we get the nicest patterns of attention here. So you can also play and just use some other image from the internet, and this is going to work. So that's the idea with this Jupyter. Hopefully you got some understanding of how of the things that this DETR model is learning. So you can see that we have interesting patterns going on in the encoder, so instance segmentation types of masks here. And we also saw nice patterns in the actual decoder, where we saw where the query tokens from the decoder stack are attending to in the original downsampled image features. Again, quickly, this is decoder, so the query embedding vectors attending the embedding vectors from the encoder stack. So that's this part here. So again, query vector attending the embedding vectors from the top of the encoding stack. And by visualizing that, you basically visualize where this query token is attending to, the query vector. And the second image is about grabbing the image token and visualizing where that image token is attending to over the neighborhood. So that's this particular image here. So it should be fairly simple and easy to understand. Cool, now let's start digging through the actual code base. And for that, I'll first have to check out the main branch. So I'm gonna have to check out the main branch because the collabs are, so the Jupyter notebooks are checked into this collab branch. So if I do git checkout main, now I'll be able to find the code that I need. So let's go back here and let's start debugging the main file. So I'm gonna skip a lot of unnecessary details, because the code was developed to be trained in a multi-node, multi-GPU setup. We don't care about that. We just care about understanding how DETR works. Also, there is a lot of details about panoptic segmentation, because DETR can easily be adjusted so that it works for the panoptic segmentation task. We're also going to ignore everything there. And finally, the actual Cocoa implementation details are not a part of this code base, but they are using an existing API. So we'll kind of skim through that as well. So the main focus is, let's understand the three components of DETR, the architecture, the Hungarian matching algorithm, and finally, how do we calculate those three types of losses we saw in the beginning of the video. So without further ado, let's start here. So we are going to just ignore these parts. This just prints the basically the SHA of the current commit, but that's again not vital. I'm going to skip all of this. We just grab the device. So I have a GPU, so there's going to be GPU is going to be used. So for reproducibility reasons, they set the seeds for various libraries: PyTorch, NumPy, Python's random, etc. So that not that important. Now this is where the actual important part starts. So let's see how the model is built. So we first have basically we pick the number of classes because we'll have 91 here because we are dealing with Cocoa. So as you can see here, we have 91, and then as I said, we're going to ignore the panoptic part. So now let's build the backbone. So the backbone is the ResNet 50, but let's see the a bit more details there. So first of all, we're going to build the position encodings. And the interesting part of this position encodings is going to be in the actual for function of this module. So we can just kind of skip through that. Because the learning rate is bigger than 0, we are going to make backbone trainable. Nothing fancy there. So now we form the backbone and this joiner object, which we'll see what it is in a second. So it's basically just going to join the backbone, which is going to be the ResNet 50, and the position embeddings. So let's step into the constructor of the backbone. Here you can see what happens is that name is going to be ResNet 50. So we get we fetch the class, the ResNet 50 class from the Torch Vision models. And you can see here that, so dilation is set to false. And because of that, we'll just fetch your regular ResNet 50, not the one with dilated convolution. And if you're wondering, this is what dilated convolution is all about. Basically, Here is a nice visualization of how it works. So it has a similar effect when it comes to downsampling the spatial extent. So instead of using strides to downsample the output map, you just do this type of you create this type of a kernel where it's basically dilated and you're attending only certain pixels of the image here, and that's the way you manage to downsample the output map. Okay, but that's not that important, just like a fun fact. Okay. Finally, they're using these frozen batch norms. Again, just another detail, not that crucial. It's just a common thing in these detection pipelines. Okay, so number of channels is going to be 2048. And finally, we construct the backbone base. Some more details here. Let's kind of skim through this. They're going to freeze some of the parameters. Basically, the only parameters that are going to be trainable are these layer 2, layer 3, and layer 4 blocks. Let me kind of skim over that. Click F5 to jump over all of that. And finally, we're just going to extract the features from this layer 4, and we are going to take those features and basically put them as a value with the associated key that's going to be this 0 key. Okay, so that's the reason during the pass through the Jupyter, we had to have that weird 0 key, and then the tensors, we'll see that in a second. But yeah, this is the detail why that had to happen. Okay, so finally, we just take the ResNet 50 and we call this intermediate layer getter, which is just going to make sure that we only fetch layer 4 representations from this ResNet 50 backbone. That's it. Nothing fancy there. Joiner, nothing fancy there as well. We'll see the interesting part actually lies not in the init function of the joiner, but in the forward function. Again, most of the things are going to happen in the actual forward prop, but this is just giving us some idea of how the model is implemented. So let's continue here. Next up, we build the transformer. Your standard transformer, nothing interesting in the init function, so we're just going to focus on the forward prop a bit later. Now this is interesting. The DETR part is going to be probably worth kind of skimming through. The init function, number of queries is going to be 100, as previously mentioned. We just store the transformer here. We store the model dimension, which is 256, the internal transformer dimension. We create these class embed and vbox embed. If you recall, those are going to map the output decoder output embedding vectors. They're going to map those into the distribution over classes and the 4 in the bounding boxes. Okay, so you can see here we map from 256, which is the side dimensionality of the output embedding vector. We map that into 92 because we have 91 classes in Cocoa plus 1 for the no object, for the special class. Okay, for the B box, so for the bounding box, we'll have MLP instead of a simple linear layer. This is kind of the API here is kind of convoluted, but what this says is, hey, I want the output of this MLP to be 4. I want to have 3 layers. These are the hidden dimensions of the layer, and this is the input dimension. So basically, this is some type of an MLP that outputs 4 dimensional vectors at the end. Okay, we form the query embeddings, just an embedding table, so 100 of these, and dimensionality is again 256. Finally, this is the input projection, so that's the one that maps from 2048 into 256. And we just stored the backbone, and this auxiliary losses is set to true. We'll see what it is. Basically, what it does is the following. Let me go through the notebook again. It's going to make sure that we fetch the outputs of every single so not just for the last layer of the decoder, but for all of the 6 decoder transformer layers. So that's they showed in the paper that helps improve the performance by having intermediate losses and not just the loss at the end of the decoder stack. That's the idea there. Okay, so let's continue here. Again, ignoring this part because this is just relevant for the panoptic segmentation pathway. We don't care about that one. And this is going to construct the Hungarian matcher. So that's the second important part of the pipeline. But again, the whole magic happens in the forward pass. So we're just going to ignore all of this for now. Weighted dictionary is just going to obviously define the weights for the associated loss. So this loss is the label loss, this is going to be the bounding box loss, etc., etc. So this one is going to be 5, this is 1. Again, these are just some hyperparameters that they figured out during the training. Okay, we skip again this part because that's the panoptic segmentation. And because auxiliary loss is set to true, we're also gonna have to define weights for all of the intermediate losses as well. So that's what this is gonna do. I'm just gonna skip all over this and let me print you what our weight detect is gonna look like at the end. So here it is. If I kind of pass it here, you can see that we have various different weights for a bunch of different losses that we'll have. So let's see how many losses we have. So like 18 losses, that's a lot. Like that's 3 times 6 because we have 6 layers in the decoder and we have 3 layers in each of those. 3 losses in each of those. Okay, so again, we defined here the types of losses we care about. This cardinality is not actually a loss. We'll see what it is a bit later. Yeah, let's skip over this. And finally, this is the final important layer. During the forward prop of this object here, we're going to do the matching plus the loss calculation. So that's the third component of our DETR model that we are going to care about. Okay, let's continue here. So here is how the init function looks like. We store the Hungarian metric here. We stored a bunch of different objects, nothing super vital there. So one interesting detail is that we have this empty weight matrix vector, and it has, so as you can see, the dimensionality of it is going to be, I think, it should be 92. So if I were to print this, 92. So that's the number of classes plus the no object class. And the reason we set the last, so all of the weights are going to be 1, except that for the no object class, so you can see here, that's how we specified. So for the 90, so for the last element of this array, we're going to set the coefficient to 0.1. And that's going to help us put a smaller weight on this class during the label loss. And the reason we have to do that is because for the most part, we'll have only a couple of box predictions, and all of the other ones are going to be the no object prediction. And remember, we have hundreds of predictions, so that's why we want to kind of reduce the weight for these no object predictions. That's just a common thing people do to kind of counter this class imbalance, basically. Okay, we registered the buffer, meaning this is not a trainable vector, it's a constant, but it's still a part of the model, so we want to store it in the model. So that's why we do register buffer. Again, PyTorch syntax. Continuing on, we're almost done with the DETR model. So we are almost done building the whole thing. So we just placed this object onto GPU, and then we store some post-processing. We're going to see what those are in the forward pass. Okay, finally we return back the model. So that's the DETR criterion that contains the Hungarian measure and the loss calculation. And we return back these post-processors, which are going to be more relevant during the evaluation than during training. But yeah, bear with me for now. Okay, so again, we move the model weights onto the GPU. And here, yeah, just some variable like renaming. We don't do distributed, so I can skip this. Here we calculate the number of parameters. Basically, we iterate through all the parameters, and if they require a grad, then we just find the number of elements in that particular layer. And we sum up all of those numbers, and we get that number is equal to 40-something million, I think. So let's find where the output is. So we can see here we have 41 million trainable parameters for the DETR model. Okay. What this piece of code here does is separates the trainable weights into 2 groups. One group is the backbone group, the other one is the non-backbone group of parameters. So we'll have a different learning rate for the backbone and a different learning rate for the other parameters. So again, this is what this logic does. Let's not lose too much time there. And they're using AtomW, which additionally adds the weight decay logic into the optimization procedure. Finally, this is just a special learning rate scheduler that's going to drop, but I think 10x after 200 epochs. So after 200 epochs, it's going to drop the learning rate by 10x. That's the idea. Okay, Now we need to build the COCO datasets. So let me quickly go through what's going on here. So we build the COCO. We are going to transform each of our images using various transforms, such as normalization using the ImageNet statistics. And then you can see here that we'll have some random horizontal flipping, and then either random resizing or this combination of resizing, cropping, etc., etc. So just a bunch of details, not that interesting. Okay, so we just store those transforms as well as some other processing here. Again, we'll see all of that a bit later during the forward pass. Okay, this is how the dataset was formed. By the way, I kind of skipped through this part, but let me quickly show you. So image folder is, let me print you the actual paths. So we can see here the actual path towards the image directory, and then we have the annotation file. And so what I've done here is the following thing. So I kind of took, I found this repo. I'm going to link it down in the video description. And they've downsampled the training set of the COCO dataset so that it only contains 25,000 images instead of 117,000 or something. And I've additionally literally just extracted 100 images and then created a valid annotation file that contains only 100 annotations. So those are these 391 kilobytes, these small annotation files, which are going to be valid annotation files for those 100 images. So by doing that, I have a minimal COCO dataset that helps me be able to run and debug this code without having to download like 20 gigabytes of data or something. So do let me know if you want me to share the small modifications I've done so that I have this mini dataset ready for this video, okay? So that's just a minor detail. So again, this dataset now loaded all of our 100 images and the associated annotations. That's the idea. Let's continue here. We do the same thing for validation. I'm just gonna skip to here. I'm just gonna skip all of this. Let's skip all of this, and we are back to the main function. So we have the datasets, we have the optimizers, we have the model here, we have everything. Now we need to form the data loaders. So for that, they just create some random sampling of the training data, and they're going to have sequential sampling of the validation data. Nothing too interesting. Then they create this batch sampler, so we basically batch 2 training images during training. Nothing fancy there, just standard PyTorch stuff. Finally, we create the data loaders here using the training data set, using this batch sampler, and we'll have this collate function, which is going to be interesting, and we'll see how it works a bit later. Again, we have data loaders ready, and that's it. Okay, finally, some COCO specific idiosyncrasies, so I'll just skip this as well, not that vital. We don't have any frozen weights. That's again relevant only for the panoptic segmentation. Let's continue here. We don't want to resume because that's when we have a checkpoint, which we don't. We don't want to do eval. We just want to focus on the training. Okay, here we start. So we are gonna run this for 300 epochs. Obviously, I'm not gonna show you that in this video. I'm just gonna do a single iteration, a single like a loop through the training, and let's see how that thing's gonna work. So this part here is the most important part of the whole code base. Let's step into the training for 1 epoch, and here we are. So we set the model to trainable as well as the criterion. Again, as a reminder, it contains the Hungarian measure plus the loss calculation logic. Okay, I'm gonna skip all of these logging functionalities, nothing super vital there. And finally here we start loading the images. Okay, so this is where the fun starts. Basically, let's step through this and see what happens. Okay, so we are in the COCO detection, so this is the dataset class, and we are grabbing a single image. So let's see what happens here. So we're gonna end up with, I think this image is gonna be a pillow type. So image pillow, exactly, and target is just gonna be the set addiction, like a list containing all of the associated annotations. And you can see there's a bunch of annotations like segmentation, is crowd, bounding box, blah, blah, blah. We only care about the actual bounding box. So that's it. Let's continue here. Less important details like image ID is gonna be 42415. I think that's going to be the file name. So if you take a look at the actual training images here, I think it just grabbed, 42415. It just grabbed one of these images from the training data set, took its ID, and that's what it's using as this image ID here. Nothing too interesting there. Let's continue. So prepare just kind of processes the target this set of annotations, so it's a bit cleaner. Nothing fancy there. Let's continue here. Transform is going to apply the set of horizontal flipping, etc., to the image. So that's it. So again, we just fetch the image, we fetch the annotations, we process the image, we process the annotations, and now let's continue. Let's see what happens now. So we do that again. The reason is, remember, we have a batch size set to 2, so that's why we're gonna call get item of the data set twice, and then we're gonna collate those to form the final batch. Okay. So I'm gonna skip through all of this because we saw how it works already, and now we have the collate function going on. Okay. So let's see what's going on here. So batch is going to be basically a list of tuples containing, as you can see, image, annotations, image, annotations. And instead of doing that, we want to regroup it so that we have a tuple of images and a tuple of annotations. So that's what this line does here. We unpack the batch, we do the zipping, we do the listing, and then we end up with batch that's going to be, as you can see here, image, image, and then annotations, annotations. That's all. This is an interesting part and an important part, because images, in the case of object detection, are going to be oftentimes of different shapes, and we don't want to resize them into the same dimension. We want to operate on the original images. So let's quickly step into this nested tensor from tensor list function and see what it does. So here we index with 0, which means we're going to fetch the tuple that contains the tensors of images. So let's do F10 here, and we end up in that function. Okay, so again, the images are obviously going to be of dimensionality. They're going to have 3 dimensions. So if I'm going to, let me just plot this, let me just print this. Oh my God. So we have 3, 7, 68, 11, 51. So that's the number of channels, and this is the spatial extent of the image. Okay, let's continue here. And basically here, what we do is we iterate through all of the images in the batch, and we find the maximum, basically, well, let's call it like a convex hull or a bounding box. So we find the biggest box that encompasses all of the spatial resolutions of all of the images in our data set, if that makes sense. So let me show you what I mean by that. So tensor list, we just saw how it looks like for the 0th image. Let's see the shape for the second one, and you can see that this dimension is bigger than this one, and this dimension is bigger than this one, and that's why our resultant max size is going to be the same shape as this tensor here. So if I am to step over this, and if I were to print the max size, we'll see we get, as I said, the biggest possible bounding box that encompasses all of the spatial extents. So it has to be bigger than, we basically do a max across all of the images in the batch, across this dimension and across this dimension, and that's how we get this final max size. Okay, so finally we form the batch shape into which we're going to now copy paste all of these individual images. So we end up with a batch shape of 2 and then the same shape as this one here. Then we just extract individual, so the batch size, the channel size, the height and the width. So let's continue here. We just grab the types and the devices, nothing fancy there, and we create this is going to be the container tensor, and we just initialize it with zeros. So it's going to have this batch shape as we just saw here. Next up, we're going to form a mask that's going to tell us later on which tokens we need to ignore when we pass them through the transformer, because some of these, you saw that the second image is smaller one, and so some of the tokens will have to be ignored from that smaller image. That's why we have a mask, and we initialize it initially with all ones. Let's see now what happens. So we iterate through the tensor list, so that's a list containing our images, and we iterate through the basically this container tensor, and we're just gonna copy our image into that container tensor, and then we just take the mask and we fill in the false, such that the parts that remain true are the parts that need to be padded for that image, if that makes sense. So for this first one, I assume that everything is going to be false because the bigger image has the same shape as the container. So that's why if I were to print the mask, you'll see that all of these are false. And that makes sense because, again, the bigger image is of the same shape as the container object. So let's now step through it again. So now this time mask is going to be a bit different. So you can see here that we now have true here, because we do need padding for the second image because it is smaller than the container tensor. That's the idea. And that's it. Like after this, you can see that we've successfully created this container tensor. We've stored our image data inside, and we have the mask that also knows which tokens we need to ignore later on during the forward pass. Okay. Let's see what this nested tensor is. Basically, we just store. It's a simple object that stores the tensors and the masks. Nothing fancy there. Okay, so that was this part. That was what this collate function does. And now we can return back to the main training loop. Okay, so we can just skip all of this. Let me just go back to the file here. So we were here. We just need to skip all the way through here. So F5, nice. So samples just contains the nested tensors we just saw. So we just created those. So let me just show you that that's indeed the case. If I were to print type of samples, we're gonna have a nested tensor. And if I were to reach for the tensors here and then do the shape, we'll see that that contains our images. And if I were to do, instead of tensors, I think a mask, mask and then shape, here we can see that we have a mask stored. So mask obviously doesn't need to have the number of channels because we just care about masking out certain tokens from the image space. That's it. Okay, so these two lines are just gonna push the labels and the images to the GPU in case you have one. And now comes the fun part. So this is literally the most important part of the code base. So inside of the train one epoch, these two lines are the main, the gist of what's going on. So we do the forward pass here. So we get the bounding box predictions, and then the criterion is gonna do the Hungarian matching followed by loss calculation. So let's see how that's gonna work. Okay, so we are in the DETR forward pass here, as you can see here. So because samples is already a nested list, we're just gonna skip this. And the first step is to take the images, so the samples, and pass them through the backbone. So let's see how that's gonna work. Okay, so here's the backbone. First thing that this backbone is gonna do, again, remember there is this joiner object. It's nothing fancy. So this self0, let me show you what it is. So self0 is simply your backbone. So that's your ResNet 50. So if I were to print the type of this, you can see it's a backbone. You'll later see this self1. This self1 is just gonna do the positional encoding. So if I were to replace this 0 by 1, we can see that this is just position embeddings sign. So the sinusoids from the same type of positional embeddings as from the original transformer paper. Okay, so that means that by doing this, we are passing the nested, I think this is the nested tensor. Let me kind of double check this again. So let's just take the tensor list. Yeah, it says here, the notation says it already. It's a nested tensor. We passed that through the backbone. So let's see the forward pass of the backbone. Okay, here it is, the backbone base. We basically pass so we extract the tensors, which are the images, and we just pass that through the body, which is gonna fetch us as you recall here, it's just gonna fetch us the features from the layer 4 of the ResNet 50. So let's do that. And we end up with XS. XS is just going to have, I think, one key, and that's this key 0. And we've specified it here exactly, so that this tells us, hey, if you want to access layer 4 features, access me via key 0. And that's what we are going to do. So if I were to take XS of 0, we're going to access the features, and the features are going to be, as you can see, of the following dimensions. So we have 2048 channels, and we can see that the spatial extent kind of reduced here. So it started with, we started with this shape. Let me show you what we had here. So we started with 2, 3, and the original image resolution, and we got to more channels and smaller spatial resolution, which is expected from a convolutional neural network such as ResNet 50. Okay, next up, what we do is the following. We grab the features from XS and we take the mask, and now see what we do. So we basically now downsample the mask such that this mask is no longer of the same spatial resolution as the original image, but it's of the same spatial resolution as the image features that came out of ResNet 50. Because remember, we want to know which of those image features we want to mask out, because we are going to later on pass them through the transformer. So that's why we do this step. So basically, you can see that mask currently has the following shape. Whoops. Let me see so it's called M shape. So this is the original shape. After we do the downsampling, we end up with mask shape, so 21929, which is of the same resolution as the image features that came out of ResNet 50. So let me now print mask, and you can see again we have all false for the first image, and we have some of these being true for the second image, and that's it. Okay, finally we store the image features and the associated mask into a nested vector, and we return that back basically in this out dictionary. That's it. That's the first step of the backbone. So now we just want to calculate the positional embeddings. Let's see how we do that. Again, we grab the image features and the downsampled mask here. We just store that into this out dictionary. So again, let me remind you that X is just, if I were to access tensors and print a shape that contains the image features, and if I were to access mask, that contains the downsampled mask. So that's the X object here, and we store it into this out list. Here we do just a simple positional encoding calculation, nothing too fancy. Basically, we give it the X, and it's gonna do its own magic. So a bunch of code, but that's your like sines and cosines calculation, so that we ultimately end up with this positional embedding like set of vectors of the shape, as you can see the following. So it has 2, because we have remember we have batch dimension of 2. We have the same resolution here as the image features that came out of the ResNet, and we have 256 because that's going to be the hidden dimension that the transformers are going to be using. That's why we have all of this. Okay, so I encourage you to check out this code if you're interested, but I'm just going to treat it as a black box for now. It's nothing too fancy there. Okay, we store that in this positional list, and we return that back. So that's the first step of the DETR forward pass. So DETR model again, forward pass, and we return back the image features, the positional vectors, and the mask. Next up, we just decompose the nested tensor into the source and mask. So source, again, image features, and mask, the downsampled mask. Nothing fancy there. Now this is the interesting part. So we take the source, which is, again, recall this is going to have 2048, and then the downsampled image resolution. So again, source shape, here it is. And after we apply the input projection, that's going to reduce this number of channels, as I previously explained, to 256. So that's going to happen there. And then we just pass the mask. So this is what we pass to the encoder. And then we also pass the query vectors to the decoder, and we pass the positional encodings. So let's step through this piece of code. Let's do F10 here, and we are hitting the transformer. So this is a transformer layer, this is the forward pass, and let me now show you the source that it indeed is now has 256 when it comes to a number of channels. So you can see here 256. So that's the consequence of applying that convolutional layer before passing it into the transformer. So nothing fancy there. Now we're gonna do some flattening and permutation so that we have a shape that's suitable for passing it into the transformer. So that's something I mentioned here previously. Basically, you take this, and in the raster order, you're gonna flatten out this volume into a sequence of tokens. That's the basic idea. So again, let me show you the shape. The shape is gonna be 551 to 256. So this is the batch size, this is the hidden dimension, and this is the number of tokens. And it's kind of weird permutation, but that's what the this original PyTorch implementation of the transformer expects. Okay, instead of having batch as the first dimensionality. And the reason is some optimization tricks. We do the same thing for the positional embeddings. So if I were to show you the positional embeddings shape here, we're gonna end up with literally the same shape as the source, because we wanna add them up later on. And finally, we do a similar thing with query embedding. Basically, they are initially just gonna be 100 to 56, I think. So 100 to 56, and here we just add dimension at the location 1, and then we repeat it whatever the number of batches is. That's how many times we just copy paste these query vectors, and then we end up with basically the same. So 100 to 256. Okay, we do the flattening of the mask that we can pass it into the transformer, and finally we form this target. So target is going to be, so we have the source, we have the target. Targets are going to be the tokens that we pass into the decoder part of the transformer layer. Whereas we're going to just be using these query vectors as the positional encodings that we're going to sum up with the target tokens. We're going to see that in a second. Okay, so finally, we now have encoding part and decoding part. Let's jump and see how those are going to work. Let me just see whether I have a breakpoint here. I'm going to add a breakpoint to forward post. Post because we're going to have layer norm applied after the residual connection, not before. That's why we have this forward pre. So we're going to just be using this version of the function here. Let's see whether I should add another. I should probably add breakpoint here as well. So now let's do F10, just step over. So as you can see here, this is your encoder layer. We do for like 6 times, because let me show you the length. We have like 6 of these, as you can see here. So we're gonna 6 times just apply the transformer layer, and we pass basically the source here. So those are the image tokens just flattened out, and we pass the mask. So that's the mask that we got as the output, if you recall, from the backbone. And finally, we add the positional encodings. Let me now go into the actual layer. So let's see what's going on here. So we sum up the positional encodings. So those are the sinusoids we computed. We sum them up with the image tokens, and we get the queries and the keys. And then we're just going to do a self-attention, as you can see here. So the only difference is that the value vectors will not contain the positional encodings. That's it. And then we have this the part where we mask out some parts. So let me show you how this looks like. So it's mostly false, but then there are some parts that are true, which means we're going to ignore those tokens, because if you recall, that part of the image is non-existent. Let me quickly explain what I mean by that exactly. So remember that we passed 2 images into our DETR. So we had image 1, and we had, I'm gonna just draw like something like this, that's of the same shape as this one here, but instead, so the second image was maybe like this. Okay, so that means that we have to pad all of these tokens out. we have to ignore all of these tokens. And that information is now stored in this mask because it's going to be set to true for all of these image tokens. So that's kind of just a visualization I have in my mind when I think about this. So let's go back here. Let's step through this, and that's just going to be a single step of self-attention of image tokens across each other. Then this is just your regular transformer logic. We have this inverse bottleneck MLP, so nothing fancy there. I'm not gonna lose any time doing that. So let's step back here and let's continue with the decoder portion. So I'm gonna click F5 and we're gonna get to the decoder. Okay, so we end up with memory. The memory is going to be of the same dimensionality as the input source tokens. So source tokens, again, those are the image tokens, are of this shape, and you can see that the memory is going to be of the same shape here. Okay, and again, memory is just, let me show you the image here. So that's going to be the tokens we get here. So we start with image features here, and we end up with the tensor that has the same dimensionality as the input image features. So that's where we are at the moment. So now we need to pass through the decoder part of the transformer. So let me show you how that's gonna look like. We pass the target, which is gonna be initially all zeros. We pass the memory, so that's the output of the encoder. We then pass what? We pass the mask, so that we know which tokens we should not attend to when doing the cross attention. Positional embeddings, query vectors, bunch of details there. Basically everything that we have in this image here is going to be passed into the decoder. So object queries, positional encodings, memory, targets tokens, which are not displayed here but all zeros initially. So all of that needs to be passed into the decoder layer. So now let's go back here and let me step over the let me just kind of add like a breakpoint somewhere here. So here, okay, let's now click F10 and we're gonna hit decoder part. I'm gonna ignore this. So let's step through that code. So here we are in a particular decoder layer. So here how it works, we have the query positional embeddings. So those are these positional embedding vectors here. So we're going to add those to the target tokens, which are going to be all zeros initially. So we end up with query and keys being equal to those query embedding vectors. Again, we have 100 of those. Let me print the shape here. So we have 100 of those, and dimensionality is 256. Okay. So then we apply, as you can see here, we just apply a self-attention. So those query vectors are going to basically self-attend to each other. And nothing super fancy there. The interesting part in this decoder layer happens actually at the cross attention module here. So here, as you can see, again, we are adding the query position to the target tokens, and we use as keys memory, so that's the output of the encoder, and we add the positional encodings on top of the memory tokens. And we use as the value vectors the memory vectors. So we're gonna somehow combine the outputs of the encoder to form our novel representations after this. So target 2. Okay, and again, we'll be passing the padding information, so the masking information, because we do not want to attend all of the encoder outputs, because some of them are non-valid, because some of them stem from the parts of the image where we just added padding. So it's like going to be black if you look at the image in the image space. Okay, so that's that part. And then we just have regular transformer logic, the MLP part, and that's pretty much it. Okay, guys, so we're just going to repeat this 6 times. And as you can see, we're storing the intermediate representations for the auxiliary loss I mentioned. But yeah, let me now step over and let's get to this part here. So if I were to click F5, let me remove the breakpoint here. We are now finished decoder, we got decoder output. So let me show you the shape of the output here. We have 600 to 256. So why does this make sense? So 100 is because we have 100 query embedding vectors. 2 is because we have batch dimension of 2. 256 is the dimensionality of the embedding vectors throughout the decoder stack and throughout the encoder stack. And finally, we have 6 because we have 6 decoder layers, and we're storing all of the intermediate representations because we're going to apply this auxiliary loss a bit later. So that's it. So this is the thing we're going to be using, this HS, after we do this transpose operation. Okay. So finally, we apply the class embedding. So that's going to map our representation HS from this shape into, we're going to have, instead of 256, 92, because that's the number of classes plus the no object class. So let me show you the shape of the output class. So this is going to be, as I told you, 92 here. Then we do B-box embed. So that's the MLP that's going to give us the outputs, like the bounding box coordinates. So let me do F10 there, and let me show you the shape. So here is the shape. We have 4 here as the output, and that's it. And finally, we grab only the last. So this is going to grab only the output from the last decoder layer. And then we're gonna store all of the intermediate representations inside of coupled with this particular key here, auxiliary outputs. Okay, so we store the classes, the logits, we store the bounding boxes, and then we store all of the other ones, excluding the last one inside of this basically dictionary. So let me kind of step over that, and if I were to show you the keys here, these are the keys we get, but then inside of this key we have this list with all of the other outputs. Yeah, hopefully, I know this is a bunch of details, but do let me know if you get anything out of this video, and even if you watched all the way to here, like, congrats, like this was like very I can assume very like intensive, and so I'd be super happy to hear the feedback of all of you guys who stuck all the way to here. So let's continue. That was the one of the most important parts of this whole code base. Now there is a second part which is much easier. We're gonna soon finish up this video. So let's see the Hungarian matching algorithm and the loss calculation. So let's dig into it. So here we fetch just the outputs from the last layer of the decoder. We ignore this auxiliary outputs. And finally comes the matcher. So this is the Hungarian matching algorithm. Let's see how this thing works. Fairly simple logic, to be honest. So let me kind of explain what's going on. Okay, so first we are gonna grab the batch size and the number of queries. It's gonna be 2 and 100 here. Then we're gonna flatten out the prediction logits. So again, prediction logits, let me show you the shape here. This is how it looks like, 292. We're gonna flatten out the first 2, and we're gonna apply the softmax instead of using unnormal as logits. So let me do F10 here, and so we end up with a shape 292, as you can see here. We do the same thing for the bounding boxes. So I do it here. Let's now do this. It's gonna be 204. As you can see here. So we just flatten across all of the batches and across all of the like tokens, and now we'll be able to compare that to ground truth. So here's the ground truth. We trade through this targets dictionary that contains the annotations, the ground truth annotations. We grab the labels and we concatenate those. So we'll have 2 of these for the 2 of images, and we end up with, I think, 16. I already went through this code. So it's 16 because we have, like, I think 2 labels for the first image and 14 labels for the second image. So that means 2 bounding boxes for the first image and 14 for the second one. We do the same thing here. We just grab the bounding boxes, the ground truth bounding boxes, and we end up with 16.4. Let me show you the shape here. So 16.4. And now for the fun part. So this is the fun part of this whole logic. So what this thing is going to do is, so we take these 16 ground truth indices. So this tells us, as you can see on the screen here, that the first bounding blocks class is 7, and then the second is 1, and then 53, 53, 53, etc. So for all of the 200 boxes that we predicted for the batch size of 2, we're going to take those particular 16 logits for the 16 ground truth classes and extract them into this cost class matrix. Okay, so we're gonna end up with what? 216 instead of 292. So again, we start with outprop being 292, and we end up with having a subset of those with 216. Okay, so we'll see why that makes sense. Then we do the following. We calculate the distance between all of our predicted boxes and the target bounding boxes. So this is just going to do L1 distance, nothing fancy there. And again, we're gonna end up with a matrix that's 216, and it contains basically the distance between each of our 200 predictions and each of the 16 ground truth labels. So we'll know basically how far away each of them are, like a fully connected graph. Okay, if I click F10, let me show you and convince you that we have the shape 216. So quickly, what this distance function does is, let me show you. So it's a L1 distance between two bounding boxes. So imagine we have one bounding box that's like, maybe here is one, here's one. So we have a bounding box here, and let's imagine we have a second one here. Okay, so okay, that's it. And now if you were to represent this bounding box as a vector, let's use the xy representation. So that's we're gonna end up with having, so that what's the coordinate of this? X coordinate is 0, y coordinate is 1, then we have x coordinate is 1, y coordinate is 0. So this is gonna be a representation for this bounding box. And then we have this bounding box here, which is gonna be what? X coordinate is 2, y coordinate is 1. We're taking a look at this point here, and then we have 3 and we have 0. Okay, so now as you can imagine, how L1 is calculated is you basically subtract these two vectors, and so you'll end up with what? You'll end up with like, and you take the absolute value. So you'll have 2, 0, you'll have 2, and you'll have 0. And then I think you just add that up, and so you end up with like 4. So the distance between these two is going to be 4. And so we do this for all of the predicted boxes and the ground truth boxes. That's it. That's the logic we apply. And then we have this, and I'm going to ignore the implementation, but we just find the same type of so the intersection over union logic I think I mentioned an hour ago or something. Okay, so we end up with this cost matrix that's also 216. So after that, we sum up all of those matrices, and we have associated weights here, 5, and we have 1, and we have 2. So what's the semantics? What's the idea? Why are we doing this? Well, the idea is the following. We're trying to match the predicted box with the ground truth box. There is multiple angles at which we could look at this. So we can only focus maybe on what's the closest one. But then if they are close but the class is completely off, is that a good match? So if on the other hand we had, so let me show you what I mean by that. So imagine this is a ground truth box here. Imagine we have a ground truth box here, and imagine we have one box that's predicted like this. It has some significant overlap, but the class of this one is maybe cat, and the class of this one is maybe dog. And now let's assume we have a different bounding box. So that bounding box has a little bit less overlap, but it has a correct class. It's cat. So which one is a better one? Which one of these is better match? So there is no correct answer, and that's why we have to kind of combine both the intersection over union, both the distance, both the class to form the final matrix, and then solve this basically graph flow problem to find the optimal assignment. So here, so we finally have the cost matrix, and then we just kind of change the shape of that matrix so that we have, let me show you here. So we have 216. Now we collect sizes because we want to separately match the prediction bounding boxes from the first batch with the ground truth boxes from the first batch from the first element of the batch, and similarly for the second one. So we want to have, those are completely orthogonal. So that's why we have to do this separation. So sizes is just going to be 2 and 14. So 2 and 14 because we have 2 bounding boxes for the first image and 14 for the second one. Okay. And now we just do this split over sizes, which is basically going to split this into 102 and 114. So the 2 separate problems, as I mentioned before. So let me see whether this is going to work. If I were to print this and allocate it to A and B, let's print shape of A and let's print shape of B. As you can see here, this is what we get. Okay, and after splitting, you can see that we have this indexing by I. It's going to be 0 in the first iteration and then 1 in the second one. So that means we'll be grabbing only the 0th batch here and the first one here, and then basically doing this assignment problem on 102 cost matrix and 114, and it's literally your minimal flow type of an algorithm. So this is what this linear sum assignment is going to find. So it's going to find such a choice of edges in the bipartite graph so as to minimize the cost. And so what I mean by that, let's for example take the 114 one. So what is going to happen is we have a matrix that's like, let's say 114, okay, and it tells you how, so this row here tells you the cost between this particular predicted box and all of the 14 ground truth boxes. And so you're going to have like what's the cost between each of those. And so how you can visualize this matrix is the following way as well. So imagine you have like literally 100 nodes here and you only have 14 nodes here. And so we have a fully connected graph. Okay, something like this, and then we have it, all of the edges are connected here. We have a bipartite graph. And so the idea is to find 2 such edges that will minimize the cost of this bipartite graph. So hopefully that makes sense. Plus there is a constraint that you cannot pick edges that go to the same node. So you have to cover all of the output nodes. So you have to cover both this node and all of the other nodes and this one. By doing that, you literally found for each of the node, you found some ideal match. So maybe you found for this one, maybe this one is ideal, and for this one, some of these ones here is ideal one. So that's the idea. That's the Hungarian match algorithm. If you just think about it a little bit, this should make sense. It's not that hard. Okay, let's get back to the code. After we run that, we'll end up with a set of indices, and we'll see what we get here. Basically, you can see that the bounding box 17 is matched with the ground truth bounding box 1. The bounding box 66 is matched with the ground box 0. And all of this is for the first image in the batch. And then for the second image, we have 4 and 11 are matched, 7 and 1, 26 and 10, etc., etc. So we got our matching. That's it. That's the Hungarian matching. That's the second component. Hopefully this was clear enough. Let's continue on. Now we just need to calculate the losses, and we are pretty much done. That's everything there is to DETR. So we just calculate the number of boxes so we can use that for normalization. Nothing fancy there. That's going to be 16 for our particular batch. So that's 16. And now we do the loss computation. So let's dig into this. So we have 3 losses we're calculating. One is labels, one is boxes. We'll see that boxes actually encompasses 2 losses, and then cardinality is not a loss per se, but that's just an implementation detail. Let's kind of dig into this. Okay, so loss labels is the first loss. What do we do here? We grab the predicted logits. So that's going to be the output of our decoder stack, and the shape is going to be this one. Okay, so we have 100 tokens, 92 logits, and we have 2 batches. We grab this, we call this function, which is going to basically give us how we should index this output here so as to get those boxes we just found using the Hungarian matching algorithm. So those predicted boxes that are matched to the ground truth boxes, that's what this IDX index is going to contain. So you can see here, box 17, 66 all the way through 99. Those are the ones that were matched with our ground truth boxes. Next up here, we're just going to take the indices we got from our Hungarian matching algorithm. We're just gonna focus on the ground truth indices, ground truth bounding boxes indices. So let me remind you. So this is the ground truth bounding box indices. We're just gonna focus on this one and on this one. And why we do that is this is just gonna be a permutation for the labels. So we want to now permute the ground truth labels so that we have exact match with the predicted boxes that match those ground truth boxes. So let me go through that. So we end up with basically 16 classes there that are permuted in exactly the right manner. Next up, we create this tensor of target classes that's going to be of the following shape. So 200, and it's basically going to contain 91 across all. So it's going to just contain 91s everywhere, and that basically means that currently these are the classes that our output bounding boxes should have. But then we just copy paste the actual target classes. So now let me print you the target classes here. You can see that some of them are now correctly. Whoops, what have I done, man? Let me just do that again and not click anything. So let me show you what we have here. So now you can see that we basically, for the match boxes, so let's find the first ones. So 53, this is the first predicted box. So it's gonna be 0, 1, 2, 3, 4. So the fourth predicted box should be of class 53 because that predicted box is matched with a certain ground truth box. Okay, that's the basic idea. Again, I'm just gonna kind of skim through this. This is a lot of details already, but hopefully this gives you some understanding. And now we just do the cross entropy loss, which is going to force such that all of these classes have a probability that goes up to 1. And we also have this weighting for the all of these different classes such that the no object class, which is this 91 thing, has lesser weight in the cross entropy, which makes sense because you can see how many of these are there. Okay, let me quickly show you in the OneNote what this exactly means. So just to make it a bit clear, imagine we have our output here. Let me just change the color here. Let me first erase this thing. So this is our output. We have 100 outputs here. I'm gonna just picture that a bit differently. So imagine we have 100 outputs here. I'm gonna just write down maybe 4, okay? And imagine we have 2 bounding boxes. So we have one blue one, and we have one that's a green one. So now, imagine that we matched this one with this one, and imagine that we've matched maybe the second one with this one. So if the class for this one is 23, and the class for this one is like 15, let me change the color. So if the class for this one is 15, we'll want to make sure that the logits here, so that for the whatever the 15 index is, so we will have like 92 here. So this is going to be 92 outputs. We'll want to make sure that we push the distribution such that we have a peak around 15, because that's the ground truth class. So that's what this loss is going to enforce. It's going to enforce that the logit distribution for this particular output token, right? Because remember, we have output tokens, which then we map into both the boxes as well as this distribution. So this is going to push that distribution so that we have the correct class. Similarly for here. So we'll make sure that for this particular class, for this particular token, that at 23, we're going to have a peak. So that's what this loss is about. Hopefully this kind of helps it a little bit. Okay, let's continue on and see the second loss. The second loss is going to be the boxes loss. So I'm just going to kind of quickly go through this. We get the predicted boxes here, we get the target boxes. We just calculate the loss between the sources boxes and the target boxes by doing the L1. I already explained that in OneNote. and then we just do some normalization with the number of boxes. We do a similar thing here, so just generalize box IOU. That's the second component of the loss, and we just do some normalization, and those are the two additional losses that we have. That's it. And the final one is this cardinality. That is just going to tell us how many how many errors do we have when it comes to computing the no object boxes. Okay, so basically it tells us for each of the 100 predictions, how many of those were different from the no object class. So that's what this thing here does. So let me show you, let me print this here. You can see that because the model is still not trained, pretty much all of these, none of these predicts the no object bounding box, because currently it's just kind of random. So basically, if I were to print this thing, let me see what we get. So as you can see, none of these is predicting 91, which is the no object class, and that's why we get 100 here. And now we just do L1 loss between that and the target lengths. So we expect 16 boxes, 2 and 14. And so that's it, like just calculating that type of discrepancy between the ground truth and the predictions. Nothing fancy there. That's it, guys. We just repeat the same procedure for all of the other 5 layers of the decoder. I'm just gonna skip all of that. Okay, here we are. Those losses are now computed. And finally, we just use that weighted dictionary to sum up. So for all of the losses, as you can see here, we go through the weighted dictionary, we go through the loss dictionary, and if we have a corresponding weight in our weighted dictionary, we just multiply those and we sum them up and we get losses. So you can imagine that this is like probably the most complex loss I've seen in my life. Like let me see what's the length of this thing. Number of keys here, 18. So we have like 18 losses in total here being computed. That's it. And after this is just some boilerplate, to be honest. We just grab the loss, final loss. We do the 0 grad, so clean the gradients of the associated parameters in the torch computational graph. We do the backward, which is going to compute the gradients for the loss we just computed. We just do some gradient clipping with 0.1 max norm, and we do a step of the optimizer. Guys, that's it. This is like the longest video I ever made. I'm experimenting. I'm super curious to know how many of you followed through the whole video. This is probably the last video I'll make that's this long, unless I get a very good feedback on this one, because it takes a lot of time to prepare these, and it takes a lot of time to film and to edit super huge videos such as this one. In any case, I really hope you learned something new. I would super appreciate your feedback. Do let me know. If you like this video, please share it out. That's the best way you can help out this channel. And finally, subscribe to this channel if you haven't. In any case, until next time, bye bye.